This week, we interpret the results of a research study using confidence intervals, p-values, and hypothesis testing, which are referred to as the statistical inference methods. And lastly, we will differentiate between association and causation. If an epidemiological study is thought of as an exercise in measurement, the result then should provide an estimate of an epidemiological quantity. For example, a case control study might be undertaken to estimate risk ratio or rate ratio between use of cellular phone and the occurrence of brain cancer. Say we had a point estimate of relative risk of 2.5. What does this mean? This point estimate of 2.5 quantifies the estimated strength of the relationship between the use of cellular telephones and the occurrence of brain cancer. To indicate the precision of the point estimate, we use a confidence interval, which is the range of values around the point estimate. A wide confidence interval thereby indicates low precision, and a narrow interval would indicate a high precision. A simple research question we will be posing in the following slides: that does a new drug reduce blood pressure more effectively than a placebo? When we say reducing blood pressure, we would take a summary measure of blood pressure in the two groups: those who were administered the new drug or those who were administered placebo. And we would measure mean blood pressure in each of the group. So we can formulate our hypothesis and say, it's a plain English, I suppose it should be easy. The mean reduction in blood pressure with the new drug is equal to the mean reduction with the placebo. Or alternatively, we can say the mean reduction in blood pressure with the new drug is greater than the mean reduction with the placebo. So before formulating hypothesis, null or alternative, we define statistical hypothesis testing. What is statistical hypothesis testing? It is a term used to describe the process of deciding whether to reject or not to reject a specific hypothesis. Generally, we will be referring to the null hypothesis in our slides following. In research term, average, as I have mentioned, refers to the most common measure of central tendency and represents the data's central point or typical value. Statistical test in our example determines whether the averages of the two groups are significantly different. But mind, the groups can be not two groups, it can be three groups, it can be four groups. So the methodology then is a little varied, but we will restrict ourselves to the two groups. Statistical hypothesis testing is predicated on statistical significance. Now, how does that statistical significance come from? It comes from p-value. In our example, we prefer to have testing for the null hypothesis, as I said, which is average reduction in blood pressure with the new drug and according to our null hypothesis, that is equal to the mean reduction with the placebo. Hypothesis testing is a fundamental method in biostatistics used to make inferences about population parameters. When we say population parameters, because in a research setting, we are having a small sample size and we would like to apply those findings to a larger population of similar type. So hypothesis testing thereby makes inferences about that big population based on our sample data. So what inferences we make? Either we say there is no effect, null hypothesis, or there is difference between the two groups. Making evidence-based decision is a must in medical research, and thereby we evaluate the effectiveness of treatments and interventions and determine association between risk factors and the outcomes. Null hypothesis significance testing is the most common method to perform statistical inference. When evaluating null hypothesis, we aim to answer. It is a little bit of a revision that was our sample drawn from a population consistent with the null hypothesis, which is there is no difference between the two types of treatment on average BP. I repeat, we assign a null hypothesis to our research saying that there is no difference between the average blood pressure in the two groups. In one group there is a medicine, new medicine, and another group there is a placebo. So we are saying that there is no difference between the two types of treatments, and this sample we are saying is drawn from a population consistent with the null hypothesis. That means we are presuming that this null hypothesis is existential in the population, the parent population or the big population to which we tend to compare to. We can formulate our hypothesis in the two ways. Null hypothesis, mean reduction in blood pressure with the new drug is equal to the mean reduction with placebo. And alternate hypothesis, the mean reduction in blood pressure with the new drug is greater than the mean reduction with the placebo. The null hypothesis, we do not set out to prove the hypothesis. Instead, we set out to disprove or reject the null hypothesis. After all, we have received a funding, we are doing a research, we are hoping that the new drug is more effective than the placebo effect. So we are there to disapprove or reject the null hypothesis. So how do we disapprove a null hypothesis? The null hypothesis in our example of blood pressure, where we assume there is no difference between the two types of treatments on average BP, is predicated on statistical significance. That statistical significance is determined from p-value, p probability value, p or probability value, using an appropriate statistical test. When we are comparing the two averages, and the sample size is not as large, it may be made 25, it may be 30. So we use generally t-test for comparing the means of two independent groups, wherein one was administered placebo, another one was administered a new treatment. As to why we have to use t-test is because we do not actually compute the probability that the null is true. If we had a mechanism wherein we could say null is true, the probability is so much, then there was no need to go for this hassle. So we have to go indirectly because we are not able to compute the probability that null is true initially. So let me recap. A null hypothesis is a statement that there is no effect or no difference in a particular situation and is often used in scientific research to test whether any observed effects are due to chance. Another example of setting a new hypothesis in Australian health. Maybe we want to test if a new diet program helps reduce obesity rates in Australia. What would be the null hypothesis there? The new diet has no effect on obesity rates in Australia, would be the null hypothesis. Which means the researchers assume that the diet program does not change obesity rates, but are internally very inclined to reject it. And if they are able to reject it, they would like to say that, well, we found in our study that certain type of a diet program changes obesity rates. So how nice of them. So what they will do is, when they have established this null hypothesis of no difference, they will collect data and perform statistical tests to see if they can reject this null hypothesis. If they find significant evidence. Now, what is the evidence? Evidence is the probability of what they found being due to chance has to be very small. How much small? It has to be less than p-value 0.05. This is the general p-value cutoff we use. That's why I'm saying, although we can have less than 0.01, we can have more extreme 0.001. So when we are talking about 0.001, we are punishing our study that there is practically, we are in any case going to accept null hypothesis unless until the chance is very, very little. So general p-value of 0.05 is the alpha, what we call as, is the cutoff which we use to find the probability of our finding being due to chance. It's a busy diagram in here. On the right side, there's an illustration. Because why we are showing these things is that we are now computing probability that the null hypothesis is true in our null hypothesis significance testing. So this diagram, I just want to reiterate, is that the mean of a normal distribution is 0 in the middle, and it has a difference of freedom, means this of is equal to infinity. In other words, there is a very, very large population size. Very, very large population size. And on the other hand, if we compare this, it's a mathematical summary in a way of the population basically. If we compare, see the bluish one, the graph, it is a little wider. And the red one is even more wide. So what does this infer is the more the wider the graph or the curve gets, it is no more a standard normal distribution, that means with a very, very large populations, while as it has to have a specific distribution which is called as t distribution, having a fatter tails than the normal. So distributions are no more infinity, distributions are based on the sample size. In case of a blue, the sample size was 14 and the difference of freedom thereby is n minus 1. N is 14, minus 1 is 13. That means if we are able to have information about 13 observations, we can find out the last one. So the freedom is there, difference of freedom is equal to 13. Likewise, in case of a red one, it is even smaller. Difference of freedom is just 2. It has been obliterated a little bit in this showing. Okay. So previously I highlighted is that we use t-test. Why we use t-test? Because we have inability to compute probability that the null hypothesis is true. So why compute t-test when we cannot compute probability is because we are taking the support of t distribution. So t distribution support means that we at the moment have in our example where we are having two groups, we are having two averages, and we are having a x bar value, which is the difference between the two average, two sample mean difference, which is x bar. So we have a sampling distribution. Sampling distribution means what? One more, we can have one sample, we can have another sample, we can have third sample, fourth sample, fifth sample. So this is a sampling distribution of our sample means differences. So there will be different sample mean differences every time we pick and choose our sample. Now because we lack the probability distribution for x bar for this sampling distribution, we approximate this sample mean difference to t distribution. So t distribution, because they are statistical, they have statistical properties, they are very well defined. Like as I said, the normal distribution with a difference of freedom of infinity and mean of 0 and a narrow bell-shaped curve. So we calculate this t statistic, which is in the diagram in the form of equation, which equals the mean, the two sample mean difference x bar, subtract that, the two mean difference x bar, subtract that with 0. 0 because that is the t distribution or the sample distribution or the normal distribution curve. We have a 0 in there in the population. And we weight it with standard error. So what is standard error is sample size divided by square root of the number. Sample distribution, sorry. S is sample distribution. Sample distribution, standard distribution around the mean difference divided by the sample distribution divided by the number. So in this way, when we compute our t statistic, we apply it to the t distribution, which is in a form of table with rows indicating the difference or difference of freedoms, and the columns indicating the significance levels, and the matrix is having a t-test value. So we see where our t-test value is in that distribution. Thus, in our example of BP difference between the two groups, given the two different treatments, we approximate sampling distribution of the two sample mean difference to t distribution, and t statistic is calculated based on the sample mean, sample size, and standard deviation. And we make a decision on a chosen significance cutoff level. Generally, as I told you, is we keep it 0.05 alpha. Therefore, by systematically applying hypothesis testing, researchers can draw reliable and valid conclusions from their data, contributing to advancements in medical science and public health. This illustration, this slide has a repetition wherein we are saying in the first place is that we approximate probability distribution of the two sample difference with a t distribution, obtaining a t value of x bar minus 0, which is the population mean, divided by standard deviation upon square root of n. And as I said, the t distribution table looks like, which I had previously said, the difference of freedom is in the rows 1, 2, 3, and the p-value is 0.25, 0.1, 0.05. So in here, p-value of interest is 0.05. So we see in a certain case where the difference of freedom is 2, we have a t statistic of 2.90. So this is an illustration again how to show how we refer to those charts manually. Although nowadays the machines do the work for us, and when we are doing the work in a statistical software, p-value is itself drawn from the statistical software. So to determine the difference between the two groups, two-group mean BP is not due to chance. P-value is calculated from the sampling distribution of the estimator and t-test and compared to the alpha of 0.05, which represents the probability of rejecting the null hypothesis when it is actually true. So if we reject this null hypothesis and when it is actually true, if you see the column under truth of H0 of null hypothesis, in the second row or the second row of the truth one, we see type 1 error, and the decision, our decision is to reject the null hypothesis. When we reject the null hypothesis, we would be making a type 1 error if in fact, in truth, there is no difference. Alpha of 0.05 says we are going to divide the sampling distribution of x bar into two parts, the inner 95 and the extreme 5. And if our t statistic, which we have obtained by the formula shown in the illustration, falls within the extreme portion of the sampling distribution, we reject the null hypothesis. Let me say it differently. If the obtained t statistic is in the extreme tails of the sampling distribution, demonstrated by a p-value of less than 0.05, we conclude that it is unlikely that our sample results were drawn from a population where the null hypothesis is true. Maybe it was not that simple. I put it differently. We reject null hypothesis saying there is no sufficient evidence to suggest the new drug is more effective in reducing blood pressure than the placebo. Statistical testing is dependent on the family of data distribution. For example, t-test is dependent to t distribution of data. Z-test is dependent to normal distribution of data. Confidence intervals. Confidence interval. Let's talk of generally used in the medical research as 95% confidence interval. So 95% confidence interval indicates how well we have estimated a population parameter. Narrower confidence intervals indicate greater accuracy. So practically what it means is if we were to repeat the study many times with different samples, 95% of the 95% CIs would contain the true value. How should we disapprove a null hypothesis? We need to understand the p-value of the study finding. P-value is the probability of how likely it is that any observed difference between the study groups is due to chance. Higher the p-value, the greater the results occurred from chance. And lower the p-value means lower, less than 0.05, less than 0.01, 0.001, etc., etc. The less likely the result occurred from chance. Let's revise again. To disapprove a null hypothesis, you need to follow, in summary, these steps. Number one, state the null and alternative hypothesis. Let's talk of null hypothesis again. Null hypothesis typically states that there is no effect or no difference while the alternative suggests that there is an effect or a difference. Collect the data then. Gather data through experiments or observations relevant to your hypothesis. Third step, choose a significance level, alpha. This is the threshold for rejecting the null hypothesis. As I said, we commonly set it as 0.05. So that means we will be looking at less than 0.05 to reject the null hypothesis. Perform the statistical test. Statistical test using an appropriate test, t-test for example, for the small samples, chi-square test in another proportions to analyze the data. This will give you a p-value. And then we compare the p-value to the significance level. If p-value is less than or equal to alpha, we reject the null hypothesis. If p-value is greater than alpha, we fail to reject the null hypothesis. Rejecting a null hypothesis means that our data provides strong evidence against it, suggesting that the alternative hypothesis may be true. Strictly p-value definition. It is a measure used in statistical hypothesis testing to help determine the significance of our results and represents probability of observing our data, or something more extreme, assuming null hypothesis. P-value only tells us how likely the data that has been observed is to have occurred under the null hypothesis. Think of a p-value as a way to measure how surprisingly your data is, assuming a certain hypothesis is true. Simple analogy. Imagine you are flipping a coin Relying solely on p-values for statistical analysis can be problematic for several reasons. Misinterpretation. P-values are often misunderstood. A p-value does not measure the probability that the studied hypothesis is true or probability that the data were produced by random chance alone. Threshold issues. The common threshold of 0.05 is arbitrary and can lead to binary thinking, significant or not significant, which oversimplifies the results. Effect size. P-values do not provide information about the size or importance of an effect. A small p-value might indicate a statistically significant result, but the actual effect size could be negligible. Sample size sensitivity. With a large enough sample, even trivial effects can become statistically significant. A significant p-value in one study does not guarantee that the result will be reproducible in another study. Focusing only on significant p-values can lead to selective reporting, where only favorable results are published, skewing the overall understanding of the research. Instead of relying solely on p-values, it's better to consider them alongside other statistical measures such as confidence intervals, which give you a range around the point estimate, effect sizes, and the context of the data. This holistic approach provides a more comprehensive understanding of the results. So the confidence interval is a range of measurement that illustrates how precise the measurement is, an interval around the point estimate. A confidence interval is a range of values derived from sample data that is likely to contain the true population parameter, which we are talking about, for example, in our example, the mean difference between the two groups. In an Australian study, another example, assessing the average daily physical activity of adults, researchers calculate the average number of minutes spent exercising per day in their sample. They want to estimate the true average physical activity for all Australian adults. Sample mean 45 minutes per day. For 95% confidence interval, 42 to 48 minutes per day. Interpretation was the 95% confidence interval means that the researchers are 95% confident that the true average daily physical activity for all Australian adults lies between 42 and 48 minutes. If the study is repeated multiple times, 95% of calculated confidence interval will be expected to contain the true population mean. So the key points, p-values help determine the significance of your results. A smaller p-value indicates strong evidence against the null hypothesis. Confidence interval provides a range within which the true population parameter is expected to lie. A wider interval indicates more uncertainty, while a narrower interval indicates more precision. Australian health examples, P study, examining whether a new smoking cessation program in Melbourne is more effective than the existing program. P-value of 0.02 concludes the new program is likely more effective as there is only a 2% chance of seeing such results if there were no difference. Confidence interval, measuring the average BMI of adults in Sydney. 95% of were having a confidence interval of 20.5 to 21.5. So what was the conclusion? The researchers are 95% confident that the true average BMI of adolescents in Sydney is between 20.5 and 21.5. These examples illustrate how p-values and confidence intervals are used to draw conclusions from health research data in Australia, providing valuable insights for public health and clinical decision making. P-value and confidence interval, in case of a dotted line, the modest effect was there, odds ratio 1.5, but it was statistically significant because it crosses the gray line, which is a vertical gray line of null. And the second one is a potentially strong effect, which was 2.5, but it's not statistically significant because it has crossed the gray line. So p-value in here tells us is how likely it is our results happen by chance. A less than 0.05 suggests our results are significant and not just random. And confidence interval, it gives us a range of values within which we expect the true value to lie. A 95% confidence interval means we are 95% confident that true value is within this range. If a p-value is low, indicating significance, the confidence interval will not include the null hypothesis value. Both tools help us decide if we are finding such statistically significant. There is an illustration in here where both of those graphs, both of those distributions, they are crossing the null of 0, or in case of a relative risk, it is 1, null is 1, where there are relative risks or odds ratios. So we see the first study is showing a p of 0.07, while as the second study is showing a p of 0.046. It is primarily dependent on the sample size in here, which elicits the difference. But which one would you believe now? So we may observe an association between two factors in a study. Whether we believe that the link reflects a causal effect is a matter of what we infer from our study, placed in context of all pertinent knowledge. Causal effects are very difficult to prove. because there are set of criteria, indicators which need to be fulfilled before we declare that there are causal effects. Association indicates the relationship between the two variables and does not imply that one variable causes the other. It can be identified through observational studies. Ice cream sales, for example, and drowning rates are correlated, but ice cream rate consumption does not cause drowning. A third variable like hot weather may influence both. Causation indicates that one variable directly affects another and requires rigorous evidence, often from experimental studies. Vaccination programs reduce the incidence of disease, has been demonstrated through controlled studies and historical data. The rooster crowing does not cause the sun to rise. The rooster crowing is associated with the sun rising. Is a crux of the illustration what association and causation looks like. Observational study in Australia finds an association between high blood pressure intake and obesity rates. This is an association example. We say while high blood pressure intake is associated with obesity, other factors might have played a role. And if it would have been a causation example, an Australian randomized control trial tests the effect of smoking cessation drug on quitting rates. The drug significance increases quitting rates compared to placebo, establishing a cause relationship between the drug and the smoking cessation. Any questions about the setup and content? You may go through your textbook and enjoy the weekend.